Hello class, this was going to be the last video that we make for this semester, and this one is on the chi-squared test of independence. So this template is downloadable. If you go to Canvas and go to Files and go to the Excel templates, you should find one that says chi-squared independence. So first of all, you might be wondering, what is a chi-squared test of independence? And so here's a little prompt. At a game night, there were 3 choices of games and 3 choices of snacks. 4 choices of games, rather. Not sure why it says 3. And the table below showed how many people had each combination of favorite game and favorite snack. So test the hypothesis that the choice of game and the choice of snack were independent. So when we have a test of independence, you can say the null hypothesis is that the game choice and snack choice are independent, and the alternative hypothesis is that the game choice and snack choice are dependent. So you can also do this for the test of homogeneity, which is just the null hypothesis is that both populations have all the same proportions, and the alternative is that the 2 populations have different proportions. But all the calculations, whether it's a test of independence or a homogeneity test, end up being identical. So you might ask, well, why is the null hypothesis independent? Well, if you remember back in chapter 4, we said that 2 events called A and B are independent if and only if the probability of A and B is the probability of A times the probability of B. And so if they're independent, there is one specific probability that you would get. It's what you get by multiplying, whereas there are infinitely many probabilities you could get if they were dependent, because literally any other number as a probability would imply that they're dependent. So back in chapter 4, we sometimes had these contingency table problems, and we asked, are these 2 variables independent? And we just looked and saw, is the probability of A times the probability of B equal the probability of A and B? Although in that case, it was just sort of binary outcomes. In this case, we have more categories than that. And we are also now considering, well, maybe the variables really are independent, and it's just that the difference from being independent is due to random sampling error. And so if we assume that they're independent, we can actually find the number that we would expect to have of every combination. It would just be the row total times the column total over the total total. And I think, well, why would that be? Well, say we want to get the probability of poker and the chips and dip. Well, that would just be the probability of poker multiplied by the probability of chips and dip. Assuming they're independent, you could just multiply those probabilities together. Well, if you did that, you'd get 25 over 115, that's the chance of poker, times 41 over 115, that's the chance of chips and dip. And so if you say, well, what's the number of people who have both poker and chips and dip? Well, then you just take that probability and you'd multiply it by 115. And notice in doing so, you cancel one of the 115s, and you get the row total, 25, times the column total, 21, and then divided by 1 copy of the total total. And so that's why that works. All right. So let's go up here and fill in the table with our new numbers here. All right, so I'm just going to delete all of these values in here. All right, and fill in the values on this chart. All right, very good. And so now we filled out the chart, and we have the totals here. So it automatically computes the totals for us just by summing the row. So you just do equals sum, and then just put in the entire row. And you can do equals sum and put in the entire column. Now over here, for the totals, notice the total is just referencing the total above here, because the row total and the column total must remain constant, what they were before. And so now we need to calculate the expected values. And so notice we have here J13. So J13 is here. It's the row total, times B21. That's the column total, divided by J21. That's the total. And notice that there are dollar signs in specific places. That allows us to copy and paste this down. So if we were to sort of empty this out and redo it, we could say, okay, so I want this to be the row total times the column total divided by the total. And then how do I want it to go when I copy and paste it over? Well, when I paste this into B2, or sorry, if I paste it into actually C13, which is in A1, B2, I would want to have the same referenced row. I still want that 25, which is the J13, which means that I do not want the letter J to change. So I can put a dollar sign on the J13. But when I go down, I do want to change to J14, so I will not put a dollar sign on the 13 because I do want that to change. Similarly, if I look at this B21, when I go to other columns, those are still going to be in row 21, so I want to put a dollar sign on the 21 to keep the 21 fixed, but I do not want to put one on the B because I do want to have reference C21 and D21. And then lastly, this 115 is always going to be the same no matter what, because the total is the same for every entry. So I'll put dollar signs on both entries now. And now I hit enter. And so then I copy and paste, and I paste it down. And now I have this full table. And I can just ignore that there's all these zeros. The expected value is 0 because there is no variable there. All right. So now we can talk about how to compute the chi-squared statistic. And the chi-squared statistic is calculated the same way that it is with the goodness of fit test. You subtract the expected and the observed. It doesn't matter if you do E minus O or O minus E, because when you square it, you'll get the same result. And then you divide by the expected. And so for this top entry, the B1A1, I would just do the B1A1 here, and then minus the same spot for the observed, and you square it, and then you divide by the expected value, which is right here. And then you do that for all of these. And in this case, when you copy and paste, you do want to move entries over in both directions. And so you don't put any dollar signs here. And so then the chi-squared is we just add up all these values. Now, if I just hit equals sum and select all the values, I'm going to have an issue because we get all this divide by 0. Now, what I could do is I could just do sum and grab the good values. And in an older version of this template, that's exactly what I did. However, what would be nice is if I could just select this entire table and ignore all of these divide by zeros. And that way I don't have to reselect the range every time that I create a new table that's a different size. And you might wonder, is there a way to do that? And there actually is. So if instead of doing sum, you write sum if, and then you can select the whole table, but then you add comma, and this very specific text. So in quotation marks, you put less than greater than, number sign, and then div/0, and then exclamation mark. The exclamation mark is important. And what this text tells Excel is do not include any cells that look like this, that look like divide by 0. So this means sum if it's anything where you don't have a division by 0 error. And that's it. And that means that we're good. So it just ignores all the division by 0 error cells, which means that it only sums the ones from our table, which is what we want. Then we can get the degrees of freedom. So the degrees of freedom is you just count the number of row variables, or it's really row categories, and you subtract 1, and you count the number of column categories, and you subtract 1, and then you multiply those together. I also have the categories here. So in our column, we have 4 entries. In our row, we've got 3 entries. Right. The p-value, just like it was for the chi-squared goodness of fit test, is the chi-squared distribution's right tail from the value and the degrees of freedom that we have. And then also we can do the significance level and find a critical value the same way that we did with the chi-squared goodness of fit test, where we use chi-squared inverse right tail, and then we just put in the significance level and the degrees of freedom, and there's our critical value. And so we've done part B here, find the values of chi-squared, degrees of freedom, and the p-value. That's all good. And so then the last question is, what can you conclude at the alpha equals 0.05 significance level? And so there's 2 things I could look at here. I could either say the p-value is less than 0.05. So they are dependent. Or I could say that the chi-squared is greater than 12.59.